Welcome. Today's topic is representing numerical data. If you haven't already seen my video here on understanding binary numbers and conversion to decimal and understanding how to determine the value of a binary number, please check that out first. Today's topic is meant to build off of what we already know about how a computer stores numbers. We know that we can use transistors to use base 2 to represent values, and we know that we can do this increasing the amount of value that we can represent by using another transistor. And the more transistors we use, we keep doubling the amount of values that we can represent. Now that's great, but it only covers a small amount of the actual numbers that we use computers to represent in the real world. What about negative numbers? What about decimal numbers? What about scientific notation? You're going to find that as we move on from here, we understand now that we have these transistors and we can use them to represent some kind of values, but the analog world around us is full of things we need to represent. Not only do we need to represent numbers, we need to represent words, we need to represent images and sounds and videos and all kinds of things that need to be brought from this analog world around us into the digital world of our computer. Numbers are the easiest to explain and work with, and that's why we're starting there, but numbers themselves are not as simple as converting to base 2 and using the transistor. We still have to figure out how to encode real integer and real number values that we use in the real world into our computers. And that's what our talk is about today. Let's start with understanding the basic data type. In a programming language, you've probably used, especially if it was a statically typed programming language, such as, Java or C++ or TypeScript even, you've probably used data type. And data types give you a specific type that you are creating for a variable. So if I create an integer type variable and I put a number into it, I cannot save a string into that, at least not in a statically typed language. In a dynamic or loosely typed language, you can. What are these data types and why do they matter? Well, the short answer is it's how we encode the information on the computer. So if you're going to store an integer number, you may be able to store that, not likely, but may be able to store that as just a raw binary number or an unsigned binary number, as we discussed when we talked about just binary numbers. However, more likely than not, you're going to have to deal with negative numbers. Positive and negative numbers make up the set of whole or integer numbers. But there's also real numbers. Real numbers are a step beyond that. We have numbers with decimal point. We have numbers whose magnitude exceeds the computer's capacity to store it as an integer. Normal computers have 32 or 64-bit word sizes. You might declare a type, and especially if you think back to like C as a double or a long, and these specify the amount of bits that you would have to, in this case, specify a real number. These things matter because all data types have a specific amount of bits associated with them. Even in JavaScript, which is a dynamically typed language that uses the type number to represent all numbers, has 64 bits in which to represent a number. If you exceed that amount, you have gone over the amount allotted. In learning how to represent these things, we're going to start with value or magnitude, and then we're going to work up to sign and decimal point when necessary. Starting with the easiest, which is binary equivalent, I will start off by saying this is very seldomly used to store actual numbers on the computer. This is nothing more than the idea of what we've already talked about when we discussed base 2 and encoding, so to speak, although we're not really encoding at this point, we're just using another base to describe a value. So if we have the value 10 in decimal, it's 10 in decimal in base 10. And if we have the value 10 in binary, it's 1010 for 1 in the 8's place and 1 in the 2's place. And this is binary equivalent. There's nothing new or different here. We just know that our range is determined by the number of bits available. If we have an 8-bit range, we can store 256 values, or from 0 to 255. If we have a 32-bit range, we can store 4 gig or 4 billion values, specifically 4,294,967,295. And don't forget 0. Now, once the numbers get this big, we of course estimate their size in saying 4 gig or 4 billion. This is very common. Now, an interesting side note here, while I have 32 bits up, is before the last decade, many computers were 32-bit. In fact, before like the iPhone 5S in the mobile world, all phones were 32-bit. So that meant that standard, without doubling the size of a value for any, say, an integer or something, the amount that a computer could use, address, whatnot, would be 32 bits or 4 billion worth. One of the ways this manifests was in the amount of memory you could put in the computer. So 32-bit computers, unless they had, and there was ways kind of around this limit if they really needed to, say for servers and stuff like that, but for desktops they generally did not. 32 bits, if that was used for your memory addressing, also limited the range of how much RAM you could have, how much memory you could have in the computer. 64 bits gives us exabytes, so that's a much larger number. So it's important just to note before we move on that unsigned binary is only a whole number integer and it is unsigned. We have no way in unsigned binary, which is the direct equivalent example, of representing a negative number or a decimal point or anything like that. Just as we learned in our conversion videos, if we take a decimal number, we can represent it in binary and vice versa.